give it indeed a time period at which it should actually exchange information. Yeah. And if you have a tight online coupling, you have that by default every single calculation. Okay. So what can Delft3D do? Well, basically everything that Delft3D4 can do. So it calculates flows under the influence of tide generating forces, wind fields, density gradients because of temperature differences or density difference, temperature, salinity, this kind of stuff, and waves. So a nice example of salinity, temperature, and other constituents is again a paper by Mick. Man has done a lot of work in San Francisco Bay. So this is San Francisco Bay, and this is actually a transect going from the Golden Gate Bridge up to Suisun Bay, I think. Correct me if I'm wrong. So this is actually the salinity that was measured by a ship. So a ship sailed from the Golden Gate Bridge all the way to Suisun Bay, like the mouth of the delta, and it measured every so many stations, it measured vertical salinity profile. And they did that a number of times, and then they made this really cool 3D flexible mesh model, of which you saw a bit earlier, a few slides back. And they tried to mimic this 3D behavior of salinity intrusion in the bay. And actually they have, if you match the two time steps with each other, they actually got really nice results. So this is actually a validation study with real observations of 3D salt dynamics in a very large system using flexible mesh. Yeah. So you nicely see how the salinity front, which is represented by this yellow line here, is represented not only in space, so where it's actually located, but also nicely the curve of that is represented. So, nice work, Nick. Or Rose. Okay. So, other functionality is what I said about the coupling. So we have an online coupling to Wave. Not only Swan, but we also now in FM have a X-Speech-like wave model that is actually an online coupled model, like that exchanges information every time step, not every so many time steps like Swan. There is an online coupling now that's brand new, and I don't think it's even officially released, with water quality. So that's a change from Delft3D4, and we have this offline coupling with Delft3D Eco. And to show you that FM does as nice as Delft3D4, I have this nice breakwater case that you know by now, but in FM. So what we have is this 1.5 meter wave coming in from here, straight on the coast. There's a little breakwater here, and because you have differences in wave heights on either side of the breakwater and behind the breakwater, you have a flow that's actually going this direction and this direction, but because of continuity it can only go offshore, where it meets the breakwater, and then it has to go sideways, so you get these circulation cells as a result. Yeah? That's a little bit what happens. So, really cool. And then, of course, we have salmon transport and morphology as the last step. So it's also the same as Delft3D4. It even shares the code with Delft3D4 to a large extent. And this is also one of the latest and greatest results. So this is our Bangladesh delta model. So this is one grid. So this covers 300,000 cells or so, I think. So this is the Indian border here and here. So this is the Brahmaputra, this is the Ganges River. These come together. So this is the Meghna, this is the Sundarbans, where these really nice tigers live. And this is a very, very active dynamic area with a lot of mud. So we're actually now doing this big project where we are modeling this on different scales, spatial scales. So this is our macro model, and we also have smaller models of domains of this.
Is this modeling for the tidal waves or the
This
river flow?
This models flow. So we have discharge boundaries here and here. We have tide boundaries. Well, this domain is larger, so I cut it off for the figure. But we have tidal boundaries on the southern part. We have a wave model that's on top of this. So that and we also have wind. So we have wind, waves, discharges, tides, sediment transport, and morphology as well, covering like half Bangladesh.
What about the sediment formula in flexible mesh? Is the same like Delft3D?
Yes, so the morphology module is written in a way that it has generic data structures that can be used in Delft3D and in Delft3D flexible mesh.
And here also I can add any equation I want, or like.
Yep. Yes. There is indeed the option to have your own transport formulation. Yeah, you can do that in flexible mesh. To round this off, I also have a nice erosion sedimentation plot. So this is about 5 years of morphological change. Basically because the model was that far. So this is all fresh and latest and greatest, cutting edge research. So but it's really nice. It's actually performing nicely. Okay, so in terms of physics, of course, every model, you know that, makes shortcuts and has assumptions. So for flexible mesh, that is the same. So what do we assume? First of all, we assume the shallow water assumption. That means that any physical process in terms of hydrodynamics that you model, that the horizontal scale is a lot larger than the vertical scale. So if we take our tidal example again, the tidal wavelength is 1,000 kilometers, but the typical depth of the North Sea is about 100 meters. So that adheres to our shallow water assumption. Yeah? So the only thing you have to remember is the depth should be a lot smaller than the horizontal scale of the problem. Yeah? Then the second thing we assume is that we don't, well, it's a little bit related to the fact that we don't, or we have negligible vertical accelerations, so we also don't take variable density into account as a force in the vertical. So the only driving force due to density gradients is in the horizontal. So that's called the so-called Boussinesq approximation. We also assume that water is incompressible. It's not a gas, it's water. Right? And to close our equations, so we use Reynolds averaging. Everybody knows what Reynolds averaging is? Reynolds averaging is that if you have a velocity, you can decompose that in a mean component and some turbulent fluctuation. Yeah? So we can model the mean component and we have to parameterize the effect of this. That's Reynolds averaging. Yeah? And that means that basically this whole line means that we need a turbulence model if we work in 3D. So be it an algebraic one, a k-epsilon one, or some other variant, we need a turbulence closure, which allows us to calculate turbulent quantities that then can be converted to a vertical viscosity that closes our equations. Because we need a vertical diffusion term in the 3D equation. Yeah? So that's what this last line means. So it's basically you model until a certain spatial scale and everything that's...
But this is only in 3D.
That's only 3D, yeah. You also have horizontal diffusivity or viscosity, but that is the same in 2D and 3D, basically. But in 3D you need closer to concept. So what it means is you measure or you model up to a certain spatial scale, being your grid cell size, and all the processes that are smaller than your grid cell size, you parameterize them using a turbulent. That's the idea of this Reynolds averaging concept. Yeah? Is that clear?
Yeah.
Right. So then a slide that you've seen before, I think, on Monday. To be clear, so basically what we solve is a momentum and continuity equation. So as you probably know, momentum just says that water doesn't move until you apply a force to it, right? That's what this means. So this has different terms. So the inertia is the first one, so that's basically the change of velocity in time. Then you have the advection term, and these two are the total Lagrangian velocity change. So this is a Eulerian representation of the equations. Then you have the Coriolis force. You have a water level gradient. We have some external forcing that can be anything from wind to waves to you name it. Then we have our horizontal diffusion term. And we have the texture stress. And if we work 3D, we have another vertical gradient here, and we have the vertical diffusion additionally. Yep. So what can this external forcing be? Like I said, we have tide generating forces. So for example, there is a flexible mesh model that covers the entire world. It's called the GTSM, Global Tide and Surge Model. And that is forced typically by astronomical forces. So that generates its own tides based on these known tide generating forces. And that also has wind fields covering the entire globe. So you can not only calculate the tides, but also storm surges and so on. So you can apply, or you can add cyclone tracks in it, and you can calculate the effect of it. Or you can actually do this with ensembles. So you can throw in 1,000 cyclone tracks and see what the probability distribution of a storm surge is. Right. So this is possible with flexible mesh. It's impossible with Delft3D format. So you can make a hydrodynamic model covering the entire world with a seamless grid, basically. So it goes 360 degrees around. Another example is vegetation resistance, and I will not go deeper into that because you will have a lecture on that tomorrow. I just put extra. And you have wind stress. And we use a quadratic friction law for that, and I also made a nice presentation to sort of demonstrate that. A nice video. If I can find my mouse. Where is my mouse?
You also can do it.
Oh, there you go. So what happens is these gray arrows, those are actually spatially varying wind fields, or a spatially varying wind field. So it starts at 25th of December, and the wind field is constant. So it's always the same during the entire simulation. We start at 0 water level. When we apply the wind field, we go to sort of stationary equilibrium, where the water is pushed against the corner here because of the wind blowing in that direction. And at the end of the simulation here, if we go back to our equations, then at the end of the simulation we are in a stationary condition, which means that this all drops out. Coriolis doesn't matter here in this case. We have an external forcing, we have a water level gradient, you saw that, the red block means water is higher in one corner than the rest of the model. We don't have diffusion, and we don't take into account bottom shear stress for now, so basically what we get in the end is purely a balance between the water level gradient and the wind that's forcing the water level. And that's what you get then. So in the end you get a nicely stationary. So this doesn't change anymore for the last hours of the simulation. So you get a stationary situation. Yeah. This is very hypothetical. This is a closed box. It just nicely shows you the principle. Okay, so those were the momentum equations. To close the system, we also need mass balance. So again, you know what that means. That basically means that if you take the box in the water column, then the change of the water level in that box is basically the net sum of the fluxes to the size of the box, and potentially some source. So if you have the side of a box and no water is coming in, or if you have a box with a certain water level and nothing is coming in to the side, but somebody is having a garden hose and putting water in it, and of course the water level will rise, and that's that. S turn that you see here. And so you have to take that into account as well. So, for example, in a model, you could have an outlet of a power plant that discharges hot water into a river. Then that would be a source for your computing equation. Yeah? Is that clear? Okay, so that was 2D. I'm going to make a little excursion to 3D as well. These horrible equations of a turbulence model. So the classical turbulence model that's being used in most models is K epsilon. I think you heard the term. There's actually a two-equation system. It looks a lot like an advection equation. It's almost the same. But you have a mutual dependence between the turbulent energy dissipation and the turbulent energy. Yeah. So the K is the energy and E is the, or eta is the dissipation. So what we're looking at again in terms of structure of the equation is that the first term is the change in kinetic energy. We have horizontal advection, we have vertical advection of energy. Then we have vertical diffusion, and we have production and production terms and buoyancy terms. And then you see that this is this provides the connection between these two, just as the K here, between these two equations. So you could imagine that if you have a stationary situation, then this drops out, advection is 0, because it's stationary, total derivative is 0. Well, let's say you don't have production or buoyancy, so then that drops out. Let's assume that the diffusivity is very small as well, because you don't have flow. Then basically your change in time is then basically your energy dissipation, right? So that sort of explains the coupling between the two equations. Okay, and what can those sources and sinks be? Sorry?
No, I'm saying I hate this equation.
You hate that equation. I have a love-hate relationship with turbulence models. Most of the time a hate relationship. So these sources and sinks, or sources and buoyancy terms, that can be a number of things. So velocity shear is one. So if you look at the water column and velocity is higher in the upper part of the water column than near the bottom, you have a vertical velocity shear. That's actually a production term for turbulence. You also have wave dissipation. So waves actually work in two ways in a water column or in a turbulence model. So one way is that a wave can break or it can whitecap. So if a wave becomes so steep, it just starts losing energy. And that is a surface source. But a wave also has orbital velocities that reach the bottom. And if you have a wave-related velocity near the bottom, you get a bottom shear stress. So that's also a production term of turbulence, but then near the bottom. Yeah? So that's the effect of waves. Then we have the regular bottom friction. So a flow going over bottom exerts a stress on the bottom. And you get classic bottom shear stress, bottom friction. Wind works a little bit the same as waves at the surface. So when wind blows over a water surface, it generates mixing. So that's also a source term. And then density, that relates to this buoyancy. So if you have horizontal or vertical density differences, then you get, that's a source of turbulence as well. Yeah. So that all these, those fill these two terms in these equations. Okay, and then you say, why would I care?
No, you skipped one.
I skipped one. Well, you should care, because turbulence actually determines the shape of your velocity profiles. And one very simple example to demonstrate that is the so-called Klopman tests. So these tests were done some 30 years ago, and those were very well described, documented, and archived, so we can still use them. So do tests, document them, archive them, and make them accessible to as many people as you can, because they will be used. And so what these tests were, so they were done at Real Hydraulics at the time. So they took a flume and they put a wave on it. Then they pumped water in the wave direction, and they pumped the water against the wave direction, and then they also did this where they just hit the wave properly on the flume. And at the same time they measured the velocities, so these are all these crosses that you see here. And what they saw is that the shape of the velocity profile depended on whether the waves were traveling against the current, following the current, or whether there was no current. Now that is the experimental result, and as these lines show, we can actually nicely represent that in Delft3D FM at the moment, thanks to months and months of code crunching, but it worked in the end. And all the dynamics can be related to the turbulence model, actually, because this is a non-breaking wave, so we don't have wave forces acting on the water column except for the effect of bottom friction, which is very small in this case. We have a little bit of streaming. Everybody know what streaming is?
A little bit of what?
Streaming.
Streaming?
Streaming. If you have a wave traveling over a bottom, you have orbital velocities, right? But if you're near the bottom and you're actually in the bottom boundary layer, then that means that this orbital velocity is a little bit faster at the top than at the bottom.
Ah, right.
Yeah.
And that means that you don't have a zero component of the vertical velocity at the moment that you have your maximum horizontal velocity. And the effect of that is a little net force in the direction of the wave propagation. So that drives a little velocity. Yeah. So that actually plays a role here, because that's this little dink that you see here. Oh. But if you look at the rest of the, so when you do have a current, then you see that for this case, the vertical velocity shear is rather low, right? Because you have a lot of shear here, but then starting from about 5 centimeters above the bottom, it's like a straight line. So the vertical shear is very low. And you also see that here, because as you have less shear in vertical, you also have less
But this is
energy.
like a specific cross section, right?
This is in the middle of the flume, yeah, somewhere.
This is the meeting point of the two directions?
No. So these are separate tests. These are 3 tests. So one where they had the current with the waves, they stop the flume, then they read the whole thing, put the instruments in again,
But
did a
how
new
is
test.
there is wave without current, like still water but with wave
Yeah.
effect?
So they just put on the wave panel without putting a discharge to the flume. Yeah. So here you see that you have hardly any vertical velocity shear, so that results also in a lower kinetic energy. And here you see that it actually, you have a changing velocity over that, so you have more kinetic energy. Yeah. So this sort of illustrates this sort of dynamics that you get when you actually start to model turbulence and which effect it has on velocity profiles. So it matters. Yeah. Okay, second 3D contribution is the sediment transport, suspended sediment transport. I think you have seen this equation in the 2D version, where I think here you had this this relaxation term by what's his name again? Sri Lankan guy. Kalapati. Yes. That one. But this is the 3D version, so again we have the same sort of stuff. So the first term is indeed the concentration, change in time, horizontal advection, vertical advection, and because we are sediment, that falls under the influence of gravity. We do not look at the vertical velocity on its own, but we also take into account the settling velocity of the sediment. And additionally, we have a horizontal diffusion. So if we have a diffusion in our flow field, then we also will have horizontal diffusion of the concentration. And the same for the vertical. So if you have vertical diffusion, which we can calculate with our K epsilon model, for example. So if we have the K and epsilon, we can calculate the vertical diffusion profile. Yeah. That is a factor times k squared divided by epsilon, I think, from the top of my head. Well, then you can calculate these vertical profiles, and most of the times this epsilon here is taken as the flow vertical diffusivity, or the same as the vertical viscosity of the flow. So you don't use something else here. Yep. And then you have seen this, I think, as a showcase how good Delft3D is in modeling 3D sediment transport and flow curves. And I claim that FM is at least as good. This is the dynamic simulation of this. So, wait, I thought I had this on remaining. Well, anyway. So I want to have this repeating. So what you see here is the flume. It's 30 meters long. It's about half a meter deep. We have the discharge coming in from this side, and we have a water level imposed on that side. We have a sandy bed here with a trench in it. And what we see in the first 5 minutes is that the flow needs some time to stabilize, right? Till we get like nicely uniform conditions. And then we put on our morphological change. So what we see here is, in the vertical, we see the concentration profile, which shows you that it's actually indeed a Rouse-like profile with high concentrations near the bottom and then lower concentrations up in the water column. Because all the sediment is mobilized near the bed, and then it needs vertical diffusion to be actually transported higher up in the water column. We also have bed load transport, which is not represented in this animation. But we have suspended transport, so in the water column going that direction, we have bed load transport here. So what we see here is then that this trench gets filled in from this side, and you also have recirculation, which sort of scours out this side, which makes the trench move nicely in that direction. So this is a 3D FM model.
But the long-term effect of, if we have a trench in the bed level, the long-term effect will be the moving of this trench, like shock wave, like erosion and sedimentation in the same trench. So it's kind of propagating of this trench.
Yeah.
But in modeling, it's like sedimentation with time, and at the end of the model, it will be with the level. So
well, not here. Well, I also must say that this you need a 3D model to get this correct. So if you do this 2D, then your trench is actually not migrating enough, and it's also deeper than what you would expect. Actually. So in 3D, it's a lot better because you need that recirculation here, that recirculation cell behind this point where the flow is shooting off to get it right. Yes? Okay, are there any questions about this? No? Everybody's still following? Ali, you still following? You look very, very hesitant. What is it you don't understand?
Some physics. And this one, the turbulence one, I confused because the two figures.
the one with the wave with current.
The one with waves?
Yeah.
This one?
No, the next. Yeah, this one.
With some wave. So this is the K, basically a plot of the K over the vertical for the three cases. So if you have only waves, then you have very little turbulence production because there's no wave breaking at the surface and there's not a lot of bottom friction because it's in a flume. So you get almost zero kinetic energy profile. But if you put a current on it, then you get additional, because then you get the effect of the vertical velocity shear. You get the effect of enhanced bed shear stress, because you have currents and waves, and those work together. So that's another production term. Does this work? So you have a production term here at the bed. Yeah? So you have production here, and you have production here at the bed. And that effect is actually enhanced when the waves are opposing the curve. Yeah? So then you can even have more, you can see that from the profile, you have more velocity differences over the vertical, which means more production of kinetic energy, which means that your K curve is higher here than in this case. Yeah? And it's always a feedback effect. So your turbulence based on the velocities of your old time level gives you a new turbulence that goes to a new vertical diffusivity or viscosity, which gives you a new updated vertical profile of the velocity, which gives you a new shear of the velocity, which is again a new production term for the turbulence. So you have a constant loop and exchange of information over time. Yeah? And then you get this sort of result. Is it clear now? So you cannot see these apart from each other. So one influences the other. So
I know. So I wanna relate it. So when the curve is decreased, this means that there is a lot of a change of the kinetic energy. So
well, the higher this, so this is the, so that there's more kinetic energy near the bottom than
near the top. So
the reason for that is that the velocity at the bottom, at the top is well, you have a water surface, so there's no velocity at the water surface, right? Or above the water surface. So there it's zero. In the water column itself, there's no wave contribution. Because there's no wave breaking and there's hardly any friction. So let's say there's no wave contribution. So the only contribution can be of density, but this is a flume test where the density is fresh water, so there's no density difference. Actual only contribution to kinetic energy production here is the velocity shear. So the difference in velocity in subsequent layers of the curve. That's what you see here. And that is bigger for an opposing current than for a following current. And you see that because the velocity profile here is almost straight up, and here it's sloping. So here the shear is big, and there the shear is almost zero. So this gives a low kinetic energy than for the following current, but a higher kinetic energy for the opposing current. Yeah? Is that clear?
yeah, better.
And then here, for both cases, you almost get the same contribution by the combined wave and flow connection system. So that's why you have almost the same peak here. Yeah?
Yeah, thank you.
Any more questions? No? Okay. All right. Then numerics. I have 3 more slides, I think, and then a new quiz. All right. In terms of administration, I've talked already a little bit about it here. You have 2 parallel administrations. So what you create in RGF grid, that's this. So you make a domain. So you make these nodes and these links. You click that and you save that, and that's what you make. But internally in the code, this is converted to this. So what you have is you have flow cells, and just like in Delft3D, the whole concept is that you work in a staggered way. And staggering means that in the cell centers you have water levels that are being calculated, and the velocities are calculated on the cell faces. Yeah? So you don't calculate the velocities and the water levels at the same point in the grid. That has some numerical advantages if you do it that way. That is a reason. Okay. Then furthermore, you have these boundary points. These are points where we actually impose values that we know from a measurement or from another model, you name it. And these give that information to this first cell on the inside. Okay. So basically all the calculations are done in these crosses and on the red lines. Yeah? So you click this and we use this. Okay? And because we're working staggered, we also have slightly different control volumes. So when I explained to you the momentum balance and the continuity equation, I said for the continuity equation you take a control volume and you look at all the fluxes that go in and out, and that gives you the change in the water level. Right? This is what you do here. So for the continuity, so the conservation of mass, you actually look at the cell itself. And it's all centered on the cell center position. Yeah? That's the ortho center of the geometry of the grid. But for the velocities, we have a somewhat slightly different control volume over which we calculate the velocity changes. So basically what we do is we calculate contributions to the velocity here, then we do some interpolation to the cell centers, and then we calculate the average of these two adjacent cells. It's a somewhat more difficult way, but you need a different control volume to do that. And then we divide everything by the area of this, and then we get a finite volume closed out. So that basically gives you then that the change of momentum is the flux of the momentum over the sides of this. So basically, the contributions from these two cells, like so, plus the forces that you actually calculate here on the links. Yeah. So the only thing you have to remember is continuity, conservation of mass is slightly different little element you look at to close the balance than for the velocities. Yeah. It's classic staggered approach. It's the same for Delft3D where you have typically you calculate the water levels here, and then you have a V component here and a U component here. So there you actually split the velocity components in two components, not in one like here. So in FM you only use one component.
Sorry, could you just repeat the second part because I didn't quite
This
the one below?
This one?
Yeah.
Okay, so we look at momentum, rho times U, times A velocity. So velocity times rho times U. So you have the net flux over the sides of the control volume here. But you see that you don't have like a physical side, which you have here, right? Flux over this side is flux over the edge of the cell. But here, you only have these values that are in the cell centers, that are known from the cell centers. Right? So what you do is you take that side. What you do is you take the value at that cell center. So for every flow link, you take the two adjacent flow centers. You multiply that by the width of this. How do you say that? This the flow the cell phase, right? So this is just transposed on either side. And then you multiply it by the distance between these two cell centers. And if you then multiply that by the depth, then you get a volume-weighted value for whatever quantity you need in your momentum balance. That's a little bit how it works.
Okay.
Yeah? Is that clear now? Okay. Alright, so if you look at this, then it also sort of becomes clear why we always stress that your grids should be orthogonal and smooth. I don't know whether that was explained to you earlier this week, or just stressed that they have to be orthogonal and smooth. Didn't talk about it?
No.
Wait, good.
We don't know the reason.
Shame on you. Okay, so a grid that is orthogonal means that the line connecting two adjacent cell centers is cutting the cell face under an angle of 90 degrees. That's right. So if this line is at a straight edge with this line, then you're orthogonal. Smoothness means that the surface area of this cell equals the surface area of that cell. I'm going to wear gloves or something. Why is this important? If you have bad orthogonality, you cannot assume that the cosine of this alpha is 1.
Yeah.
And if that cosine is not 1, then you have to take into account all the cross terms in solving the momentum balance. So everywhere you have to add a term with cosine, alpha, whatever. So that's computationally, that's very expensive because trigonometric functions are very expensive to calculate. Okay? So what we want is cosine alpha being 1, and then we're happy because then we can just drop that term from the equations. Why is smoothness important? That is because on the previous slide here, we calculate the contributions of these two adjacent cells. And if the volume or if the areas of these two cells are vastly different, then the weight, well, every time you basically take the normal average of these two, then you're actually making an error against the volume, the conservation volume, basically, right? So, but if these areas are the same, then you don't make that error. And then you can just say, we'll take half of, well, the average of the two cells. Okay? So, it's important in Delft3D 4, it's even more important in Delft3D FM. So whenever you work with triangles, probably your orthogonality needs to be an order of magnitude better than in Delft3D 4. So I think the general guideline in Delft3D 4 is 0.1 or so. Well, for triangles you need 0.01 to 0.03. Otherwise, you will make errors, or your results will be inaccurate. Very important. Okay, to demonstrate this on a regular mesh. So here you see a link that is certainly not orthogonal. So you see that this is not 90 degrees. There's other examples. This one, this one, this one. What was even here? This one is horrible. Well, you get the point. But if you orthogonalize this grid nicely, then all of a sudden these are straight edges, and then you can drop the cross terms, and then your result will be a lot better. Okay. Then I also want to finish this with a slide on 3D geometries. I don't know if you have seen this. There's basically two paradigms. You have the sigma paradigm and the Z layer paradigm. The sigma paradigm actually divides your water column in a fixed number of layers, and depending on the local depth, the thickness of your layers will change. Yeah? So then you get this sort of distorted grids, and that also has some negative numerical properties. So you might have artificial diffusion along these lines in your solution. Then somebody came up with the idea of doing this with the so-called Z layers, where you fix the thickness of your layers, basically. And you just fill up the water column until you're at the bottom. Yeah? So some parts can have 1 or 2 cells, and others can have 50. That's just the way it is. Now in flexible mesh, they're busy with making a sort of a hybrid thing, where you can actually combine these. So you can have part of your grid with only Z, then you get part of your water column with Z layers, and then the lower half with sigma layers, and so on. So it looks very fancy. It's a work in progress, but if it works, then that will be really cool to have. Is that clear?
Yeah.
Yeah. Okay, well, last slide. as in Delft3D4, you have a bunch of files that are being generated whenever you make a model. And on this slide, I sort of have summarized that to give you an overview and maybe something to look to whenever you're making a model and you don't know what is. So I listed the steps that you would typically do when you're running a model. Then I listed what sort of input they need, what sort of tools that you can use, and what sort of files they produce. Right? So if you build a mesh, then you usually start with a land boundary that spatially constrains where your mesh should be, like we saw on the very first slide with the breakwater and the harbor and so on. And that will give you a netcdf file, underscore net.nc. So that's also a difference with Delft3D4. So all the outputs in FM is netcdf, which makes it very convenient to work with all sort of tools. It's way better than the Nefis format of Delft3D4, if you ask me. So once we have a net and a bathymetry, we can impose boundary conditions, and we do that simply by drawing polygons. So we can draw a polygon along a grid boundary, and then when the model is initializing, what happens is that, so let's say you have a grid here, and I've drawn a polygon like so. And at initialization, the model will shoot out virtual links on the upside, and it finds the crossing points with the polygon. And those crossing points actually determine the positions where or that marks these cells as being boundary cells. And that generates these these stars from my previous slide, these blue stars, if you remember, the boundary ghost node stars. It generates these positions, and at these positions, we will apply them in the boundary conditions. So this is cool because you leave the polygon in place. That's what I've been stressing all morning. So you leave the polygon in place and you make a different grid, one with triangles this time. Something like that. Very ugly triangles, sorry. Like so, but still you can just shoot out these. So I don't have to change my boundary conditions. And at initialization, my model automatically finds out which of these cells are boundary cells, where it has to apply the conditions. So if you have a different design, just change the grid and all the rest stays the same. Is that cool or what? Alright, so you have a grid file and an external forcing file that contains the boundary conditions, and in combination with an MDU, which is the unstructured MDF. A lot of thinking went into those names. You can then run your simulation, and that will give you a map file, which is the trim file of Delft3D FM, and a his file, which is the 3H file equivalent. Yeah. Well, and you can open. This is netcdf, so you can open it in MATLAB, in Python, in whatever netcdf you name it. So that's very generic. So you don't need any Delft3D specific tools, which is nice. Okay, so this is a little bit the end of the theory. So what I started with this morning was this as objectives. So I think we have covered two now. So I told you a little bit about the philosophy and the principles of Delft3D flexible mesh and how it differs from Delft3D4. I also told you in which circumstances flexible mesh would be an advantage over Delft3D4 and under which circumstances it's not. So it works both ways. I keep repeating that. Number 3, we're going to do this second period. But first, I'm going to check the first two with a little quiz. So please open your e-campuses. is Quiz Delft3D FM. It's 5 questions. It's clicking a bullet, and well, it should be finished within fairly soon. And it makes you think a little bit about when to use what. Let's see how you do. If a question is not clear, I can always elaborate a little bit. And it's not marked, I mean, it's just a test result. Whether you've paid attention or not.
Something like really coastal a little, but
Sorry?
it's coastal a little, but like
Yeah, sorry.
like sometimes we
I tried to explain it.
yeah.
And please give me the heads up if you're finished. Go over them together.
I got 2 of 5.
Sorry?
I got 2 of 5.
Well, at least you got to it. Always look on the bright side.
If you wanted to get more,
Huh?
if you wanted to get more, choose all Delft flexible mesh.
That's where you're wrong, kiddo.
Okay, I finished, but it's not finished. Like I choose finish at yeah, it's here. Submit, finish. 4 or 5.
Good. Well done. Give you 2 more minutes.
Wow. I get 5.
Congratulations. He's paying attention.
So you use the technique of
Do you know why? Well, I can ask you to explain. Your
2 also.
5?
So I have
But
a
if you choose the
question.
flexible, it's always the first question. So.
Is everybody finished? Hello, you are eyes. Back of the room. Finished?
No, but you can go on.
No, I mean, just finish up. It's not a life decision choice. It's just
Yeah, okay. Finish.
follow your understanding. Okay, so everybody is on this. See if you can get some results. I have 8 attempts. John still have to submit, I think. You haven't submitted?
I haven't submitted.
No? Or you didn't, you finished, but you didn't get any of them correct. That's okay. So you didn't pay attention. Oh no, you submitted twice. You got 4 right. Eh? Okay, oh, that's interesting. So we have some of them that have 2. We have most of them that have 4 or 5. So that looks okay. And can I also see which questions were difficult?
The last one.
The last one we didn't. I didn't
I thought-
fully understand.
Okay.
Use
Can I go back and go over the questions? Okay, question 1. A client asked you to build a morphogenic model to assess the effect of an existing small marina along a straight sandy coast. There is no rivers debouching in the ocean in the immediate surroundings of the study area. Would you use Delft3D or FM?
4.
Why?
Because there is like
It's straight. You
Yeah.
don't need the.
there is no changes like expected, and I can use the Delft3 for I can like change the time step.
Yep, that's a good answer.
less expensive.
Well, the marina is existing, so there's probably not a design change, so you can make one grid. There's also no rivers in, so you don't expect 3D effects, density gradients, this sort of stuff. So you don't need 2D, 3D couple models or whatever. So you can do with a simple 2D model, and then probably Delft3D is faster. So I would choose Delft3D in this case. Question 2. A client asks you to model the beneficial effects of a controlled area for flooding along a 50-kilometer river stretch during a 1 in 250 years flood peak. There are several areas that are open for as candidates where this controlled flooding area will be implemented. Do you model this using FM or Delft3D? Why?
Because I have different areas, I can like
And I want
change
to
the resolution and the area of interest.
want to
and then-
focus here.
Exactly. So there, FM would indeed be the best option, I think.
Why? Just sorry, can you repeat why?
Because there are several candidates for areas that can be flooded. So you can use a fan and then change your grid on the fly, depending on where the choice is. Or if one choice turns out to be the bad choice, then you can make it.
Usually you don't do one grid for the whole area.
No, it's cheaper.
Okay.
And so the design decision hasn't been made yet, so you still need flexibility to approach. So then I would choose something where I can easily change grids and refine what's where.
Okay, so like for me, I think that by default, if it works with Delft3D, like I don't consider it that way. It
Yeah.
can be done with Delft3D,
It
so
can
no
be,
need
yeah,
to go.
but what is the optimal model?
Yeah.
That's the question. You can always do it. Third question. You are a research scientist interested in the hydrodynamics of a large estuarine system. Your model incorporates the confluence of two rivers in the delta and their catchments and a large bay connecting the delta to the ocean. Where have I seen that before? The question is Delft3D for the best option for this case? Question mark. Is that statement true or is that statement false?
False.
Exactly. Why?
I have a lot of areas interest in this area. Like I have a bay, I have two rivers, so it's maybe 3D, like
Yep.
3-dimension effect in many areas. So I may need change the resolutions in many areas. So flexibility.
Yep, that's right. And it's totally not inspired by San Francisco. Question 4. A Delft3D FM model grid always contains triangles.
False.
False or true?
False.
That's false.
Because you said in the lecture, if you had triangles, so sometimes you don't have.
Very good. Paid attention. Last one. Now that's the long causal one. You're a research scientist interested in modeling of ecological processes on a fringing reef in Hawaii. I'm not looking at myself. The reef flat is very shallow, but it's crossed by a number of fairly deep channels. So let's say that if the reef flat is half a meter under mean sea level and the channels are 30 meters deep or so. That's a typical what you would find on a fringing reef. Offshore of the reef flat, the depth quickly goes to more than 30 meters. So that's reef flat and then come down. To study the exchange of nutrients across the reef, you need to set up a hydrodynamic model, because a lot of the dynamics are driven by waves, by swell waves. You have to resolve the so-called infragravity waves, which are really long waves, periods of tens of seconds or minutes. And this forces you to use a grid size of 5 meters on the reef flat. That's by CFL. However, offshore of the reef, these waves are not so important. So you have the choice between XBeach, which is a model that uses the same structured grids as Delft3D, but it's also explicit, like FM. So that's a little bit the mix-up here. Or you can use Delft3D FM with its own infragravity wave model, which also has a maximum CFL of 1. Which one would you choose in this case?
The F3D,
Why?
because we didn't know XB.
And
Well, I explained you what
we
the
have-
relevant parts of the
we have different grids. One above the reef flat area, which is 5, and the other, it's not important. I can use a larger structure grid in this area, so I can use.
Yep. Well, the answer is twofold. Actually, you have channels on the reef, and these channels are fairly deep. So, small grid cells and deep water depths are not friends of each other if you work with CFLs of 1. So what you ideally want is that you have your reef flat itself at high resolution, but if you go to the reef channels, that you can coarse them somewhere so that you can raise your timescale. And then offshore of the reef, there you only have to resolve wave-driven and tidal currents. So you don't need that 5 meters there. But if you use a structured grid, you will or necessarily have your refinement in deeper water as well. And here the water is really deep because it goes to 30 meters very quickly. Yeah, so that is very bad for your time step. But if you can coarsen your resolution once you are a little bit offshore, then you can again raise your time step and have a faster model with the same results, basically. Because you resolve all the physical processes on their relevant scales. Yeah, so FN would be correct answer. Yeah.
Okay.
All right, then we can have another break, and then we'll get to do some hands-on. You all have the slides, and I really want you to work in pairs. So make mistakes together, please. And I'll be walking around, and if you have headphones, you can also watch the videos. I've made for every exercise. I've made a video that has detailed instructions, but also the PowerPoints are fairly detailed. Okay.
Yes.
So we reconvene at 11:30.